All right, the last example, example 8, we have the following two limits of exponential, e to the x and e to the negative x. So for e to the x, this is going to be infinity. We can look at the graph of what e to the x looks like. E to the x does something like this. Okay? So a little follow-up limit we can do here is we can also say that the limit as x goes to negative infinity of e to the x is equal to 0, because this gets closer and closer. This distance between the function and the x-axis gets smaller as we go to the left towards negative infinity. And this limit right here, this observation, is exactly what allows us to say this. You can almost think of it as like a substitution. So this is equal to 0. And we can also have another sort of follow-up limit. And this is the limit as x goes to negative infinity of e to the negative x. Think of it as like the double negatives canceling. And this is really just going to be e raised to a very large positive double negative number. So this would be infinity. And let's just think about what that looks like, e to the negative x. This is exponential decay. So as we move to the right, this graph decays that way. So instead of growing to the right, this decays to the right. And let's go ahead and do a quick kind of extra problem here that I don't have written in my notes, but I thought this would be a good time to talk about this little thing that can happen. So let's take a look at the limit as x goes to infinity of 5x minus e to the 4x over, let's say, well, let's not do 5x. Let's just do 5. 5 minus e to the 4x and 4 plus e to the 7x. Okay? So this is not a rational expression. And there's no polynomials or roots or anything nth power functions. So we have to think about what is the dominating force in the numerator as x goes to infinity. So what happens to each of these two terms? You have to ask yourself as x gets larger. What do they do? Well, 5 just stays 5. 5 is a constant. So regardless of where x goes or what it does or what value it attains, 5 remains 5. So this is static. Much like in the denominator, this 4 is static. Now these two exponential terms, they will change. So what's going to happen here is really, we know that e to the 4x and e to the 7x are both going to grow. And now you can think of this 4 and the 7, the coefficients in the exponent on e, they're just like scaling factors. They're going to change the amount of growth. There's still going to be very fast exponential growth, but e to the 7x will outpace e to the 4x as x goes to infinity. It's going to grow faster. If we graphed e to the 7x over here along with e to the x, it would kind of do, it would start, I think, a little bit lower, and then it overtakes it. They intersect right here at 0, 1. So it's steeper, effectively. So in this case, negative e to the 4x is the dominant term in the numerator, and e to the 7x is the dominant term in the denominator. So this would end up just being the limit as x goes to infinity, negative e to the 4x over e to the 7x. And then you want to simplify this. I can factor out the negative limit as x goes to infinity. And then remember, we can just simplify these two by, we have like bases. So the quotient of two exponential functions with like bases, we subtract the exponents, top minus bottom. So this would be e to the negative 3x. 4x minus 7x is negative 3x. And as x gets large, e to the negative 3x gets exceptionally small. So this is 0. But what happens if we take this same limit here, but this time we go to negative infinity. Because it's not a rational expression, we could get a different answer. So as we go to negative infinity, now let's think about what's dominating terms. And this is the interesting thing when you have terms that are not just rational or polynomials. There's different rules you have to think about. So again, both 5 and 4, the constants, they're not going to change. So whether x is going to positive or negative infinity, this doesn't matter at all. But these exponential terms, their behavior is different now that we're going to negative infinity. When we take x to negative infinity, the exponent on this e to the 4x will become a very large and negative number. When you look at the graph of e to the x, when you plug in a really large negative number, that means you're plugging a number all the way down to the left. This thing approaches 0. Right? It approaches 0. So actually, when x is going to negative infinity, this term becomes negligible. Same argument for the denominator and the e to the 7x. These exponential growth terms, as we go to negative infinity, become exponential decay. Right? Right? If you run time backwards, exponential growth is necessarily exponential decay. So if we go backwards, these terms decay away immediately. So in this case, the actual dominating terms are 5 and 4. So the limit via dominating terms is the limit of 5/4. 5/4 is a constant, so the limit of that is just itself, 5/4. So dominating terms, this is an example I wanted to show you that you're not always just comparing the top and the bottom. You do that when you have rational expressions, but if you have anything other than rational expressions, you really do have to have a conversation with yourself about what is each term doing as x goes to wherever x wants to go.